Hi, this is Tom Fiddaman with Ventana Systems, and I'm just doing a quick introduction to my talk today from the System Dynamics Health SIG. We missed the recording of the first couple of slides, so I thought I'd introduce those briefly, and we'll jump into the presentation in a moment. We're talking about Ventity today. Which is simulation software created by Ventana as a complement to Vensim. I'll mention a few resources and talk about why we built it, and then give you a quick orientation to some new concepts, and hopefully mainly show you some examples. Hopefully we'll have a little time at the end for Q&A. And I'm particularly interested to hear about the model representation challenges that you face and how those might or might not be served by Ventity. Or if kind of representation isn't your biggest problem, then what is, and how we could guide the software tools to serve the most urgent modeling needs. Before I get into that, I'll mention a couple of other resources. There are some video tutorials on Ventity on the Ventity.biz site. And there's also an Introduction to Ventity workshop from the 2022 System Dynamics Conference, which is available for anyone. So it's at the vensim.com conference link shown here. There's a zip archive containing finished model products. So you can follow that. That builds an agent-based model. The second is a video about doing classic system dynamics in Ventity, where you don't use the entity tools for agents or for detail complexity, but rather to support representing and exploring a lot of different scenarios on the same underlying model. And then finally, you can get a copy of Ventity from the download page. There's a free 60-day trial license. And if you have an old version, or if you've tried it before and are coming back to it, you may find that the trial license doesn't work for you. If that's the case, shoot us an email at info@ventity.biz and we'll refresh your credentials so you can try it again. So I'm with Ventana Systems. We're part consulting firm, part software firm. Our overarching goal is to serve decision makers by integrating models and data. Data used loosely to mean both time series and subject matter expertise and other forms of data about a system. In models that are robust, transparent, and fast, ultimately, we want to convince people to do the right thing. So we have to know what it is by exercising the models a lot to ensure that they're correct, and making them transparent so we can actually communicate about what are the interesting dynamics and why that should guide your decision making. Ventity was built for some specific internal purposes at Ventana. We wanted easier access to collaboration, so more modularity. We wanted better model data separation for essentially code reuse. And we wanted dynamic creation of structure and sparse matrix representation improvements, because those were burning problems in a lot of our real world consulting projects. So the target for this is actually, it's not specifically agent-based modeling, although it's capable of doing that. It's actually closer to traditional SD. So the entities in the model might be individual agents like people, but they might also be, say, a large organization or a series of departments in a hospital or something like that, where the entity is not kind of a trivial individual replicated by the thousands or millions. It might be a pretty complex structure, sort of a large sector of an organization that's replicated, you know, tens of times, not thousands of times. Some examples from things that motivated us to build this, and some of which we've since done on commercial projects. Climate integrated assessment modeling, where you have the physical sort of global carbon cycle and temperature dynamics, and then an economy hitched to that. You'd like to separate those into separate sectors interacting. It supports that well. If you have, say, a healthcare system where you have payers and providers, you may have, you know, a modest number of payers just because of concentration in the industry, and a larger number of hospitals and doctors' offices and other providers who are interacting with those, and each is serving a patient population that's migrating and churning. And the key there is that the payer-provider relationships might be pretty ad hoc. So you don't want a payer by provider matrix. You may want a sort of a sparser matrix that recognizes the fact that not all providers are in network for all payers. In other contexts, it's very natural for project modeling. It's very natural for supply chains where, you know, the beer game is literally just a single chain, but real world supply networks typically have networks of manufacturers and wholesalers and distributors and retailers with much more complex relationships among them. So any one retailer is going to be served by more than one distributor, and any one manufacturer or factory is going to be sending product out through multiple channels, some of which might go through kind of the traditional cascade from wholesaler, distributor to retailer, and some of which might be, say, direct to consumer. So these were the targets. And, you know, within that universe, there's a whole spectrum of possible ways to represent any given problem, from the very aggregate kind of classic SD view to the very detailed view. And there are a lot of pressures that push you one way or another on this spectrum. I personally, my bias is to try to stay as close to the left-hand side here, because partly it's just more fun in a sense to have less stuff and a better understanding of the model. But it also makes things run faster, makes it easier to deal with uncertainty because you can do millions of simulations and Markov Chain Monte Carlo and things like that. But on the other hand, in the real world, unfortunately, there are things that you just can't aggregate even in principle because of nonlinearities. And so you need some kind of detail. There are also cases where developing an aggregate representation of something is hard because you don't understand how to do the aggregation. You can kind of think through a priori how the individuals in the system work, but you don't know how to represent that as, say, a coflow or an aging chain or some simple structure. It may also be that you have big data that you want to exploit. You have individual level data on healthcare outcomes or something like that. And finally, maybe the treacherous one is that decision makers always want to see all their stuff in the model. So, when you're in the boardroom with the CFO and the CTO and various other kind of high-level managers in the system, they all want to see the detail in the number of servers they have in their racks and the all the detailed line items in their balance sheet and P&L and so forth. And if you don't put their stuff in the model, you run the risk of kind of the immune system rejection from the organization. But of course, this is very treacherous, because if you put a lot of stuff in the model just for the sake of pleasing a stakeholder and the structure turns out to be kind of non-strategic, then or not germane to the real question at hand, then you've really just bloated your work with a bunch of things that get in the way of actually solving the strategic problem. So I'll show you in a minute a bunch of models that are kind of at different locations on this spectrum, but using very similar representations. As I do that, here's some things to watch out for. When we built Ventity, we found that we had to introduce some new concepts. Although they're generally not new, they're kind of reused from other domains. So an entity is an instance of what we call an entity type that's very close to an object-oriented programming classes and object instances. It's also very close in the database world to tables and rows. So if you're familiar with databases, a relational database is typically made up of multiple tables. So you might have a table for customers and a table for transactions. So each table corresponds with an entity type, and it'll have a bunch of columns that represent different variables containing the data. And then each row is going to be a particular instance of a data entry. In a database, you need some way to distinguish or identify all those rows. And in Ventity, the analogy for that is attributes. So attributes are basically just text tags that identify an entity so that you can sort of refer to them by name and get information from other entities in the model. That's the equivalent of a key to a table in a database. Closely related to that is what we call a reference, which is a way of finding some other entity. So if you have a model that has, say, a network of people, each person might have a reference that points to one of their friends or their doctor or their bank. These don't necessarily need to be things of the same type. As soon as you have entities, you have collections and sub-collections of entities, so you can slice and dice all of the people by their hair color and eye color, or you can kind of divide the banks into banks and savings and loans and credit unions. You could, if you had, say, a model of hospitals nationwide, you could aggregate them up according to the city that they're in, and then the state that city lives in, and so on. as soon as you have a set of entities, you want various kind of aggregate metrics of what's going on in that set. So there's some functions for finding averages, sums, standard deviations, and so forth over those collections. And then finally, we have actions and triggers. So actions are discrete events that fire between time steps, and they can actually modify the model. So for example, you can add or delete entities, or you can modify the state of an entity by, say, shifting some stock value. And the key for these really is that they happen instantaneously between time steps, and that they can change the structure of the model. So for example, if you delete one competitor from the market because they went bankrupt, that changes the structure. Or you could create an action to, say, take two providers and merge them, in which case you would delete one and then take all the people and money and capital equipment and add it to the stocks in the other one. So that's kind of the universe. So these things aren't entirely new, but I think the package is new. Of course, you can do all these things if you are modeling in a programming language, but then you lack a lot of the other tools like dimensional consistency checking and a diagram representation corresponding with the stocks and flows in the entities, and easy visual inspection of everything that's happening in the model. So we tried to preserve the genome of Vensim in the implementation of Ventity, so you still have causal tracing and all the other things that that we like to have for kind of model quality control and rapid debugging. So just to orient you to what you'll see in a moment, this is the interface. So the kind of the core of a model is what we call the overview up at the top left, which lists all of the things that are in there roughly in the sequence that you might build them. And then diagrams are typically front and center. You have another view into the entities, which is what we call the inspector. There's one over at the right here. And then for viewing output, there's an entity picker, which lets you control what's visible on charts. And then finally, there's some kind of utilities like a list of errors and a console. So let me walk through some examples, and I'll first show some infection models, and these are actually in the sequence that installs with Ventity. And then I'll talk about a couple of real-world projects or real-world models over here on the right side as well. And again, feel free to interrupt me with questions at any point. Before I dive in, any comments so far?
I feel like I should comment about me not being here when this thing began. Normally our sessions are at 11 Eastern, and I'm in a time zone right now on vacation. It's 10 Eastern, and my brain got messed up when I sent out the reminders. And so I just wanted to apologize to you, Tom, for kind of messing up the start of things here and maybe confusing a lot of our members who are going to come at 11 o'clock thinking, well, Wayne probably just screwed that time up, which I did. But but I did get the recorder on, so most of this is going to be recorded. Maybe I'll work with you afterwards to stick a table of contents or two at the front so people know why
sure.
it is. But anyway, yeah, I didn't want to mess up the flow of your talk, but I did want to just chime in and just apologize for me goofing things up and making a mess out of what was already confusing from the time that you were going to talk last month. So adding insult to injury in some ways. So anyway, hi, for those of you who actually made it here, this is really fascinating. And I'm so glad to finally be getting into the details of Ventity. I think I'm gonna become a user finally after all these years.
Cool. Yeah, I guess one of the interesting puzzles, sort of maybe not so interesting commercially, but the challenge for us has been that the kind of the learning curve and the mindset shift are much bigger than we anticipated, even for our own use. So we're still learning a lot here too. All right, so let's take a look at some models. And again, this series, the first few that I'm going to show you here actually install with Ventity. So you have these on your disk if you go and install the trial. So I'm going to run this. So this is just a really simple SIR model. What we're seeing here is basically classic SD. So you have susceptibles, infected, and resistant. People are getting infected via this positive feedback loop. And I can control the transmission parameter here with this slider. So this is all very much like doing this. If you did this in Vensim, you'd have basically the identical result. Let's see. What's different? One thing that's different is just the way windows work, although actually Vensim is moving this way as well. So I can take any window and I can dock it somewhere else, or I can float it and close it. I have the ability still to plot everything. So if I have a chart pinned here, but if I want to plot just the infected stock, I can see that. And I have a history here actually of past charts, so I can use that as a menu to flip through things that I've visited recently. I can float that. I can also dock this. Didn't size that very well. So if I want to have larger plots, I can do that, and I can float those. But basically, this model is kind of classic SD, except that you'll notice each tab here, there's a model and a strain. So the model is an entity that exists in every model. It contains time and time step and initial time, final time, sort of utility stuff. You can put other variables in the model as well. But strain is an entity. So I called it strain because it represents a strain of disease. And if I want more strains, I can just modify the entity initialization data that sets this up. So again, if you walk through the overview here, there's entity types, and then there's a couple of macros and components, which are sort of reusable structures for building the model. There's time series data, which I can talk about later. And then initialization data is the sort of the manifest of entities that exist at the start of the model or that might get injected partway through the run. So if I look at this data table for strains, just double clicking it to bring it up, you'll notice, so here's the strain entity. I've got the flu active, but actually I've populated the model with Ebola and smallpox. And again, these are totally notional. I just reused the names, but the transmission rates have nothing to do with reality. so if I just check these boxes to enable these and run it again, now you can see that I have multiple diseases running simultaneously. So there's Ebola, the flu, and smallpox. That chart gets a little busy, so I might want to drop a simpler one on. So I'm just going to drop a chart object here, and I can connect infected to that, so you can see just the infected people. And actually, if I reset the sliders, you'll notice that the slider is now populated with 3 entries corresponding with the 3 entities that exist in the data. This is kind of the simplest possible example of the reusability of structure here, because I now have multiple instances of the same thing merely by supplying different values in this input table. And I could go through and I could create additional data sources that represented different sets of entities. So I could add a different built-in data table that had, let's say, COVID. And you'll notice there are some parameters here: the initial stocks of infected, the recovery time parameter, the initial susceptible stock, and so forth. I can override those, but if I leave them all blank, then it'll just use whatever is in the equation. So here's the equation for the infected strain. So you can see it has inflows of the infection rate and the recovery rate, which are determined by the flow pipe connections on the diagram. And then it has an initial value. Same thing for, say, the transmission fraction. That's a constant. So you'll notice that checking the constant box here puts it in the sort of the manifest of things that I could change as parameters of the model. So if I run this again with the new data, now you can see I have the COVID dynamics, and I can switch what's running in the model just by changing data sets. So that's very useful. I can show you sort of some pictures later of a model. We built a model for the city of Belmont, Massachusetts, describing their building and vehicle stock and electric power consumption and CO2 emissions. And later we took that model and we just tossed the Belmont data and replaced it with data for Shrewsbury, Mass. And it ran pretty quickly without any fooling around to change the structure of the model. We just had to replace the data set. And you could even have them both coexist in the same file if you wanted to. So that's kind of cool. I think we made a big leap forward in reusability of model structure through this kind of stronger version of model data separation. Any questions? I'll show you yet another variant of this that does kind of makes a cool use of these capabilities in another way. Okay. Let's see, I'm not going to save changes. This is actually the same model, but I made one change, which is I added a policy parameter which says that at some time in the future, you can reduce transmission. So you start doing NPIs or better hygiene, masks, social distancing, and so forth. So if I reduce transmission by say 50% in the future, you can see actually in this case it hardly affects the disease trajectory, because I don't inject this policy until day 100, where it's already more or less run its course. But if I move things up early in the infection, then I can much more strongly limit the disease, although it doesn't go extinct here. I guess I'd have to have a more aggressive reduction. So if I can get the transmission reduction high enough, I get R0 below 1. I think 40 or 50% doesn't quite do it here. I guess it does, but it's a slow peak. So you'll notice that as I change the transmission fraction, there's a red run that's changing and a blue run that is staying static. So the blue run is the base case with no intervention, and the red run is the policy run. So when I move this slider, it's only influencing the policy run. That means if I change the parameters of the disease, I can see how that intervention affects a disease that has a particular set of characteristics. So I've sort of separated the environmental or the physical characteristics of the disease from the policy response to the disease. So how did I do that? I did it simply by setting this up so that it does 2 runs every time you move a slider or hit the run button. So I have a control here called the run control, which is basically a manifest of all the runs we're going to do. So you'll notice I've set this up with a base run and a policy run. And then when I created these sliders, if you edit the properties, you can see there's a property on a slider that says ignore the first run. So that means the first run will be essentially the unperturbed base case, and then any subsequent runs here will be alternative policy runs. So that's kind of cool. We used this a lot again in that city electric power model, because we always wanted to see the base case emissions and compare, say, what if you install more heat pumps, or what if you have more EV chargers? How does that affect the outcome relative to the base case? And then we'd like to be able to look at how sensitive is the improvement over the base case to assumptions about price elasticity of demand or population growth or other things that are kind of outside the control of the electric utility, but which are important policy uncertainty drivers. So far, we're basically just doing kind of the same kind of classic SD that you do in any other tool. Now I'll shift gears to look at things in more of a new way, using some of the new representation features in Ventity. Before I do, any questions on this so far?
It just makes me wonder how do you position this? Like, for example, lots of people know about AnyLogic because AnyLogic is a true multi-hybrid kind of simulation environment. This feels quite different from that. And there's probably things that are really, really powerful in Ventity that would be very, very difficult in something like AnyLogic, and certainly can't be done in Vensim. But how do you, in your own mind, how do you organize these different ways of going at building complex models?
I think that's still, to some extent, a learning process. I mean, I guess our view of AnyLogic was that as soon as you start trying to do some of the things I'm about to show you, you quickly leave kind of the graphical world of traditional SD stock and flow representation, and you end up writing some Java code to glue things together. And we wanted to make more of that visual. So that's probably one difference. I don't think there's anything you could do in Ventity that you can't do in any logic, because it's got kind of this general purpose programming language underneath. Probably the other thing that's different is that we did pay more attention, I think, to separation of the model from the data. So I think there's some reusability advantages to Ventity. But to some extent, I hesitate to say too much, just because I'm not a regular AnyLogic user, and I'm probably not as up to date on that, certainly, as some of the other tools that are closer to the core of SD. I guess in a sense, what's the right tool, always comes back to what's your biggest problem. And so there were the problems we were trying to solve were flexibility of representation and model data separation and reuse. That may not always be the biggest problem. If your problem is you need millions of simple agents interacting, Ventity is probably not the tool for that, for example. All right, I'm gonna just open another version, continuing with the same set of models. And this looks exactly the same, because it is, except you'll notice now that there are a whole bunch of different disease strains on this chart: strain 1, strain 2, strain 3, strain 4. And if I run it several times, you'll notice that this is changing, because these are random injections of new disease strains. And actually, you can see a little bit better if I plot susceptible. So you can see here that there's strain 1. Strain 2 doesn't even exist until, this must be about day 60 into the simulation. So you can actually do this in Vensim as well, except or in I think, or other tools, except that you would have to create an array that would have all of these populations kind of provisioned up front, which means that you're simulating a lot of zeros for things that aren't dynamically interesting yet. Whereas in Ventity, we literally introduced strain 15 in September 2018, so that you don't have to simulate any of its stuff. And actually, we can also delete these strains once they reach some criteria. It's a little trickier to know when a strain has really run its course, but you could, for example, delete them when their infection rate has fallen below some threshold, for example, or when their cumulative infection stops growing. So how does this work? There's now a second entity type in this model, which I called a population. So this is the strain entity. The population is basically a description of a susceptible population, which consists of just a parameter in the number of people involved. And then it runs an action through this triangle here, is what we call a trigger. So a trigger fires an action. So there's a parameter here for frequency of strain emergence. So it's sort of how often does a new flu strain emerge. So this is just a number. So it's 1% per day. then strain emerges is a switch variable or a flag that is just a train of pulses driven by that variable, but randomized. So this is using just a random variable. And actually, I could smarten this up and show you how the equation editor works. You'll notice there's no buttons here the way there are in Vensim, and that's because everything uses predictive typing. So as soon as I type R here, I have all the random functions. So I can make this a Bernoulli random variable, which is simply a coin toss with a fixed probability. And then if I highlight the probability hint here, I can substitute frequency of strain emergence. So I've just made that a little more elegant than the if then else statement that was there. But if I run it again, it's doing exactly the same thing. So this trigger simply says, what's the criteria? So if the flag is 1, then we create a new strain. And I can go visit that create action. So this is what we call a create action. And all it does is set up the state of the new strain that's going to be created. So it's going to create a new one of these. And this has some stocks. And if I inspect it, it also has an attribute that identifies it. These aren't shown by default, but I'm going to drag this onto the diagram so we can see it. So the attribute sort of looks like a parcel tag for a reason, because it's a text identifier that lets you find this disease strain. So if I go back to the create action, it's basically just setting up the number of infected, the number of resistant, the number of susceptible. And here you see it gets the number of susceptible from that population parameter, which is number of people in the population. And I've left this blank, so it's just going to give the strains just an arbitrary sequence name. So when the model runs, every time this flag spikes, we launch a new disease strain, which means we create a new population of people with fresh susceptibles and one infected person. And then the dynamics play out over time. Actually, I can just pop this chart out. You can use this in lots of ways. If you were modeling you could do it actually. So this is the interesting thing here, is this is kind of a hybrid model. You have disease strains as the entity, so you still have aggregate people. And actually, you'll notice the parameters of each strain are a little bit randomized, which is why these peaks vary in height every time. You can use this for kind of hybrid aggregate discrete, but you could also do it to launch individual people into an emergency room or something like that, in which case the flavor of the model would be more like a discrete event simulation. And I'll show you an example of that in a moment.
Hey, just a quick question.
Yeah.
These are not interacting with each other, right?
These are not, but they certainly could.
Okay.
So one thing we could do, for example, here's the strain collection. I can create a new aggregate, which is, say, the sum of infected people across all the populations. So now if I run this, this is going to look like a single curve that's kind of spiky. So that's the total infected population. And now I could say, feed this back into something in the model. I could either have infections spilling over from one population to another, if you were thinking of these as a bunch of cities. Or I could say use this as the emergency room loading, and it would affect the quality of healthcare for everybody across the portfolio of diseases. And actually that question's a great transition point to yet another view. Suppose here's one way of kind of looking at those crossovers. Same model, except I've added mortality here. And if you look at the chart of infected here, what you see is I've set this up with a bunch of age cohorts. We did a paper about dynamic cohorts at the SD conference a few years ago, which talks about how this works. So in this case, we have a bunch of populations that represent 10-year age cohorts. So every 10 years, you sort of start filling up a new cohort with the babies of that generation. And then you launch a new cohort 10 years later and 10 years later. And up front, you have some existing age cohorts. So if you look at the data that initializes this model, there are people born 10 years ago, 20 years ago, 30 years ago, 40 years ago, and so on. So these are the historic age groups, and each one has different numbers of susceptibles. Basically, they tail off in size linearly. So when we start the model at time 0, there's no disease. We introduce an infected person in, let's see, in the 50-year-old cohort. So you can see this row of the data here has one infected person in the 50-year-old age cohort. But that quickly spreads through the other existing cohorts. And then every new generation sort of catches this disease a little bit later in their evolution. So it's sort of like, chickenpox 2.0 came along, swept through the entire population, and then it hits every new generation as they kind of age into the population. So this is actually much like the introduction of new strains, except in the population entity. What it's doing is it's introducing a new cohort at regular intervals. So this is actually, it's not too different than, say, having an aging chain for these people or an array dimension, except that, again, aging chains have a dispersion problem, and arrays mean that you'd have to create all the age cohorts up front, which means you're simulating and looking at a lot of zeros for sort of people who haven't been born yet. Here, it's a little more elegant, and in particular, it's more elegant if you want to change the cohort interval. So if you look at this chart, this is a 10-year interval. So that peak happens at time 67, and the next one's happening at time 78. So the infection peaks are about 10 years apart, corresponding with the introduction of the people. But what if I want to explore the need for finer time resolution? Let's say I need 5-year cohorts or 1-year cohorts, either because I think the dynamics require it, or because I think, because I have, say, 5-year population cohort data and it's easier to match up with that, I can just go here and change this parameter from 10 years to 5 years and run it again. Interesting. Extinguished. I think what happened? Did I change that right? I did this morning and it worked great. got new cohorts. Maybe that the infection's dying out too fast or something. All right, this is odd. Well, so presenter's curse, I'm missing something. So what's cool about this, let me go back to the population, set this back to 10. Now that's odd. I'm just going to close this and reopen it. Okay, so I'm not sure what I did there, but you can see we've now got 5-year cohorts instead of 10-year cohorts. So essentially you can parameterize the degree of aggregation in the model just by changing that one number. You don't have to mess around with changing array dimensions. And actually you could even change the level of aggregation on the fly or in a kind of model data independent way. So it makes it much easier to experiment with the granularity of the structure of the model. Here's another way to apply the same kind of structure, and I notice time's short here. So I'll just hit this fairly quickly. Imagine a different setting where you have a disease that exists in multiple hosts. So here I've set this up with humans and monkeys, and the transmission pathways are very simple, but a sparse matrix in the sense that humans bite humans, monkeys bite humans, monkeys bite monkeys, but humans don't bite monkeys, except for Ozzy Osbourne, maybe. So you have 2 species and 3 transmission paths, but there's some excluded pathways. And, there's some diseases that are kind of multi-host, in which the pathways would be even more sparse than this. So that means we now have essentially 2 things in the model. We have the species. So this chain here represents what's happening to humans and monkeys. So you can see here are the infected monkeys peaking in 2015, and then the infected humans peaking a month or 2 later. But we also have relationships among them. So we could have up to 4 relationships if everything's populated, but in this case, we only have 3. So I created an entity type, which we call a relationship entity, but it's not really special, which links one species to another species. And you'll notice here, these are the attributes that point to the species that are involved. And infections then are the crossover from one species to another, or it could be from humans to humans or monkeys to monkeys. So this is an example of what you were asking about a moment ago, the spillover from one host to another, or the interaction among the entities. So you can see on the crossover plot here, we have monkey to monkey transmission that peaks. Then you have a small amount of monkey to human transmission, but once the disease is unleashed on the human population, humans become the dominant source of transmission to themselves. So again, all of the structure here is set up by the data. So we've got humans and monkeys. so there's two tables now. There's one for the crossover. So monkeys to humans, humans to humans, monkeys to monkeys. And then there's one for the species crossover. Or there's a table for species that just specifies how many individuals there are and who is initially infected. And if we want to run this with a more complex setup, again, we can just change the data and run it again. So I have a 5 species table with more relationships. So you'll notice there are 5 species. They're just called S1, S2, S to S5. But there aren't 25 entries in the crossover table. There are only 10. So the matrix of, or the network of connections is sparse. And if I run this, you can see all the infection transmission crossovers. So these are mostly kind of own species transmission. And then there's also a small amount of, say, this curve down here at the bottom is species 3 to species 5. So the interesting thing here is that a very small amount of crossover among the species kicks off large epidemics within the individual species. So you can see the total infections by either by target species or by source. And there's a lot more that you can do with this kind of structure. I can actually show you one more model that is kind of the full agent version of this, where you have thousands of interacting individuals and a detailed social network topology. But I'll pause for a moment because I notice we're over time. I'm happy to keep going and show you more things if there's interest. But I think the key is what's the right tool for the job. So this has been a big learning process for us, and we're actually using both Vensim and Ventity sometimes simultaneously in actual client projects. There are some things that would drive you one way or another. So Vensim is still more capable in the space of advanced algorithms like Markov Chain Monte Carlo, and it has a command script and automation language, or you can use the Vensim DLL. It also does ODBC for direct database access, and it can publish a model to a browser. On the other hand, there's some things that would drive you to Ventity if you need creation and deletion of entities or other aspects of dynamic structure. If you have kind of a natural network like a doctor-patient network or a supply chain network, or your data is kind of loosely structured along a more relational model rather than a matrix model, there are a lot of advantages to Ventity. It's also easier to reuse by just replacing the data, and it has some GIS capabilities for visualization of the model output on maps. If you don't need any of that fancy stuff, then it's really more a matter of preference and experience. There's some nice things in Ventity with synthesim overrides and things like that for exploring models, but there are also some nice ways to use Ventity to do classic SD. And finally, if you can't decide, you can always start in Vensim and port to Ventity. It's harder to go back. You basically might as well rebuild the structure by hand. Sort of Ventity's representation is a superset of Vensim, so there's no way to automatically port the model back to Vensim or XMile or another tool. So that's kind of the landscape. I'm happy to show you some models of increasing sophistication or to just talk about it. And I'm particularly interested in what you think is the frontier or the burning need for model representation or other tools.
Hey, Tom, we have a bunch of new people in the room who came because they thought they started at 11 like we normally do, which again was my screw up. I'm going to apologize to all the new people. We did record this and we'll get a version of it out there. I think I'm going to ask Tom if he'll help me clean up the front end of the recording, which I didn't get the recording started until 6 or 8 minutes in. And so we'll sort of build that up and eventually we'll release a video of this. I'm happy to keep going and we'll keep the recording going as well for a little bit longer if people have questions. But I just wanted to promise those of you who came at the time we normally meet that you'll have a way to see what Tom presented, and I'll work with him to very quickly, without too much work on his part, patch up a beginning to the presentation. And I'd like to say, maybe we can have you back again down the road a little ways to do some more stuff. This is so interesting. And I know some of us are more technical and others of us are more practical. And so I don't really know, but I guess I wanted to say is thank you very much. And apologies one more time to everybody who got on this with me not having kind of organized it ideally. So let's open it up to questions and I'll stop talking.
And actually, maybe for the sake of those who are just showing up now, I should show that additional model and we could talk about that a little bit. Just so folks who just arrived are a little more oriented. How does that sound?
Well, let's just make sure if anybody has to leave, I know people.
Yeah. So actually,
let's get them take care of them, and then those who want to hang around a little bit longer, we'll just keep going.
We'll do a part 2. Sounds good.
Yeah.
Thanks, Tom. I had a question that I put in the chat, not necessarily about Ventity, but I was curious to know a little bit more about the interface of Vensim in browser.
Oh, yeah, I should. I can just show you a quick example. We haven't really publicized this very much. But it is available. So this is a model developed in Indonesia to look at greenhouse gas mitigation options and kind of the multi-sectoral impacts on water and forest and things like that. The model was built in Vensim. It's, I'd say, moderately big, several thousand equations anyway, and not a ton of array detail, but some. So, for example, in the energy sector, you've got coal, oil, gas, wind, solar, I think. This is what you're seeing on the screen here is an interface built around that, using the publish to web tool that's in Vensim. So normally when you publish, what it'll do is replicate what's on the screen that you're publishing from. So if you build an interface in Vensim, you can essentially publish that and then run it in Synthesim in the browser. But in this case, what we did was we took the core simulation engine that gets generated, which is a WebAssembly component, and we put a JavaScript and HTML wrapper around that gives you all the charts and sliders. And actually, this is an open framework, so you could reuse this same layout. You might also notice that this kind of the general shape of things is strongly inspired by Climate Interactive's C-Roads and N-Roads. they've done such a good job of creating those interfaces that actually the Indonesians came to us and said, we want that. This is a little more complex just because they have a lot of stuff in the model. So it runs in real time in the client browser. So if I move sliders here, you can see how the model changes, and you have some interactivity. So you can look at, you can change the chart layout to see different things in the model. You don't have everything that you have internal to Vensim, you know, causal tracing and things like that, but you do have a lot of control over how this interface looks. We've set this up now so that it's largely populated by some CSV tables that specify the charts and the sliders and their bounds and things like that. So you can set this up in a somewhat code-free way, but if you wanted to build one of these, it would be helpful to have and you want to go past the default publish in Vensim, it would be helpful to have a JavaScript and HTML web programmer on the team to do the work. But you could basically do anything you want using the core model as the simulation engine. There's one key limitation at present, which it doesn't do time series data, but that's going to go away fairly soon. So that's what I mentioned. In Ventity, you could do this by running the model on the server side and having the client browser interact with it. But that's A, more complex, and B, introduces a little bit of latency between the user and the server. So it's kind of better on an intranet than it would be on World Wide Web. But there are examples of Vensim models that work that way as well, like the energy innovation model that runs the model centrally on a server using the multi-context DLL and Vensim, and the interaction is pretty good there.
But Vensim doesn't offer the interface maker here, right? So the assumption is we gotta do the HTML work to create the interface. So I'm a little bit disconnected where Vensim comes, you know, in the picture. It's like, is there an option in Vensim that we go to create this, you know, online publishing interface, or?
Yes, it's on the file menu. There's a file menu item for publishing to the web. It doesn't create this. It creates a visual of whatever's on the screen in the Vensim model at the time. I don't have an example queued up, but if it's interesting, shoot me an email and I can
that was great to know. I didn't
generate
know that
something.
Thank you.
Yeah, it's pretty new, and we haven't done much to publicize it yet. Other questions? Let me show you one more or n more Ventity models. I'm going to open one that I think kind of does everything that you might want out of an infection model. And actually, this is kind of inspired by the agent aggregate comparisons in Hazir Ramandad's thesis, where he explored how the essentially the network topology among a group of individuals with some diffusion process happening conditions the outcome, and the extent to which you could represent that with an aggregate version of the model. So for people just joining us, this is the Ventity interface. It's the thing we're looking at on the screen here is the stock flow chain in what we call an entity. So in this case, the entity is an individual person. So the susceptible, infected, and resistant or recovered stocks here are not, in this case, describing the number of people in a population in a given state. This is more of a state machine for that individual. So if you look at, I can't remember if I ran it yet. If you look at the susceptibles, for example, or let's look at infected, I'm going to plot this variable. What you see is hundreds of individuals who are infected for a period of time and then recover. It exceeds the capacity of the chart, but actually I could filter this down using the entity picker here. So I can deselect all of the people and zoom in on patient 0. So there's patient 0. They got infected in October 2018, and they were infected for a week or two, and then they recovered. And those were all random events. I think I used essentially Bernoulli trials or something for those. I can edit this flow to see the equation. Yeah, so I just tested a random uniform variable to see if it was more or less than the probability of infection in order to run these processes. So with some probability, people get infected based on the prevalence elsewhere in the population, or actually not elsewhere in the population, elsewhere in their social network, and then they recover after a period of time. And same thing for recovery. I translate the recovery time into a probability of recovery per time slice, and that drives the individual's recovery rate. If you look at the collection of all the people, then you can calculate some aggregates on that population. And so here's the total number of infected people is shown on this chart. So it grows very rapidly and then tails off at essentially the time constant of the recovery rate. And you'll notice then if I run this multiple times, each time this curve is slightly different. And that's because of the randomness in the population. And I think the individual population here is probably 1,000. So this is 1,000 people. So it's not real big compared to a real population. If I ran this with 100,000 people, it would probably be much closer to kind of converging to the continuous limit behavior. And usually there are a few cases there. There's one. You'll notice there's one infected person and then it dies out. So this is one of these cases where patient 0 either recovers quickly and doesn't spread the infection to anybody else, or they have a weak social network. So they're simply not connected to many other people, and therefore the probability that they can transmit it to somebody else is low. But at least with the parameters, the way this is set up most of the time, this looks a lot like the standard diffusion curve that you get out of the SIR model, or its analogy, the Bass diffusion model. So what's happening here? So in this model, again, I mentioned we have persons, and if I look at the person, each person is identified by a person ID. And these people are automatically populated into the model. So essentially there's at startup, I generate 1,000 people programmatically. Then these people kind of look around and they make friends with other people. So they create a social network among themselves. So you'll notice this triangle here is what we call an action. which by which people search the population around them and establish connections to other people. So when they do that, they create a relationship. So a relationship is from one person to another person, and a relationship has the possibility of carrying infection from one person to another. So if we go back to the person here, you'll notice that the probability of infection for a person depends on the fraction of their contact network that is infected. And that in turn depends, depending on a flag here, there's a flag that can switch this model between well-mixed or an explicit social network. So normally I'm using the social network. So this says that the contacts depend on each person's individual exposure to infected people in their own social network. And actually I can follow this back. So this is for each target person, the fraction of contacts in their personal network that are infected. And then there's some logic in the setup of the model that lets you set up these relationships with different topologies. So you'll notice here over in the data sources, in the entity initialization data, I have a well-mixed situation. I have a ring network in which each person is connected to, you can think of the people as laid out on a circle. So each person is connected to the, if you think of a bunch of people sitting in a circle, then I'm connected to the person to my left and my right. And then they're connected to the person to their left and back to me, and so on around the circle. There's also a two-dimensional grid, and then some random networks, a small world network, and a scale-free network, which have denser connectivity among the people, but different distributions of the connections. So and actually you can see that kind of the high level view of the model here. So so the person is connected through relationships, and then infections sort of pass through those relationships back to the person. And then the population entity here just sets up, it creates the people, and it contains some parameters that are used for some of the different network topologies. So I can go back to the model here. And I can just change the data to change the outcome. So here's the well-mixed version of the model. You'll notice the behavior is slightly smoother. So we still have individual people, but every person in every time step has an equal probability of interacting with some other person. So there's essentially no social network. Here's the ring network. So again, same number of people, same transmission parameters, but the behavior is radically different. Well, in this case, the infection died out. Let me run it again. Here's the ring network. You'll notice that basically the disease proceeds more or less linearly, and that's because of the ring topology. So individuals can only expose the person sitting to their right and left. So you can think of this kind of like burning of a fuse on, a cartoon bomb. The fire proceeds linearly down the string, and it can't spread in 2 or 3 dimensions. Whereas if you have a grid, spread is more rapid because it can proceed, essentially the exposed surface of the social network grows with increasing prevalence among the individuals in the network. The grid's still limited though, because the sort of the perimeter of the network shrinks relative to the area as over time. But then as soon as you get to random networks where there's arbitrary connectivity among individuals, or small world networks where there are some teleconnections from sort of one part of the network to another, then you get much more rapid spread. So this is kind of, I think, doing all of the new things that Ventity brings to the table. It's creating people from scratch. It's creating a network of relationships from scratch. That network is sparse. So in other words, we have 1,000 people, but we don't have a 1,000 by 1,000 interaction network. We probably only have 10,000 connections. I think each person has 10 friends as this is set up. And I noticed in the chat, someone asked, can we set the parameters of that? And I think that's the case. There's a parameter here called friends per person. I don't have a slider hooked up to that, but I could lower that to 5. And if I go back to the model here and run it again, that's probably going to slow things down. Well, actually, it didn't very much. It's actually been a while since I played with the parameters, but so the short answer is yes, you can parameterize the construction of the network, or what's probably a little more typical is that you would actually set this up with data. So you'd have data on the individual entities in the system, and maybe on the relationships among them as well. And so you might drive the model off of an actual social network rather than a hypothetical social network.
Tom,
yeah, go ahead.
I have a question regarding kind of visual syntax here. Could you go back to the person tab for a second?
Yeah.
So, looking at this in sort of traditional Vensim OSD visual syntax, right? We've got the susceptible, infected, resistant stocks, and those are stocks, right? Population groups. How are we supposed to understand those here? Are they still stocks as in group, population groups, or are they states that individuals transition through, or is it a hybrid of both?
In this case, they're states that an individual transitions through. But actually, it could be both. And in fact, when I built this model, I started with the aggregate version, and I actually just reused the structure. All I had to do was change the infection rate equations and the recovery rate equation, and to reinitialize it so that there's initially only one susceptible. So there's a one susceptible person being the one person in this state. But you could certainly do this, and in fact, I have other versions in which the level of aggregation is a little different. So instead of persons being the entity of interest, you could have, say, cities. So you could have a series of cities that are where this chain is aggregate because there are 10 or 100,000 people, and then there's a network, a transportation network among the cities of trade and airplane flights and road travel and things like that. So you'd have kind of a hybrid of continuous time, continuous value infection within a city, plus either discrete events or kind of continuous transmission among the cities, but at a much lower rate. And we actually used this in the early days. I'm trying to remember exactly. We were working for a state on their epidemiological modeling team in the early days of COVID, and we built some models of schools and parents and workplaces and things like that that were kind of hybrid models. So you had, say, a classroom with 30 students in it as the unit, and then families that were at, sort of 5 arbitrary people or something like that associated with that. So there are a lot of different ways you could use a very similar structure, and the reusability of the model has proved pretty good, I'd say, in terms of being able to take the aggregate version and then quickly do the agent version. Actually, I'll just close this. In the chronic wasting disease project that I've been working on for the last 2 years, we did a lot of exploratory modeling because there's kind of a fairly rich literature on wildlife diseases. And of course, all of the standard epidemiological modeling stuff applies as well. Although prions are a little weird because they accumulate in the environment. So there's an environmental reservoir as well as the individuals who are infected. So in this model, I actually built several instances. So we were interested, do we need age cohorts, or do we need individual deer, or should we have a sort of a 2D spatial grid, or can we get away with aggregate? And we were really hoping we could get away with aggregate. So this model actually contains aggregate deer. I guess that's what we're looking at here. So here's the healthy deer, exposed, infected, clinically sick, and there's no recovery in the case of CWD. And then there's some additional processes, births, mortality in each category. And then we also added the, so if you look at one of these stocks, here's the exposed deer. So this is single aggregate stock. We also did the cohort version. So here's the cohort version. It looks exactly the same, except that the births process is moved to a different location. And you can see that prevalence is by annual age cohort. And then we did an individual deer version, in which case the individual histories are kind of difficult to interpret because they're discrete. So you want to move up to the aggregate level and look at the sum over the population of the various categories. So here's prevalence at the aggregate level. And then in the model entity, you can compare these. So here's the aggregate version versus the individual version of the deer population. And then you can quickly test, okay, if we change disease parameters or change the level of aggregation or other things, how does that affect the difference between the aggregate representation and the individual representation? And we used this to determine what we could get away with, essentially, because we wanted the model to be as aggregate as possible for transparency to the users and for fast simulation, basically.
I just want to draw your attention, Tom, to a couple of questions in the chat. And
oh, great.
And encourage Thomas to go ahead and speak that, or you can just look at the chat and maybe see if you have a quick answer to his questions.
Let's see. Okay, so running Ventity models on a server, it's more like running Vensim on a server, the way you would at, say, at Forio. So need a server to host the model, and then you need a web client, or actually it doesn't have to be a web client. It could be some custom app that can interact with that server. And I'm actually not that familiar with the technology, but basically you're using some kind of HTTP post protocol to send parameters to the server and then retrieve time series results for the variables you want to show on charts or reports or whatever. And then the related question here is that back to Vensim, the WebAssembly approach is currently kind of synthesim based, where you move a slider and see the change in the outcome. Question is, can it do turn-by-turn gaming, is what we call it in Vensim. It can't currently, although actually probably could if you were clever about how you wrote your HTML. So I think the answer is it doesn't explicitly support it, but you could hack it already if you were willing to write a little JavaScript. You could kind of handle advancing time by just changing the final time of the model in the synthesim-like environment. So I'm going to say that's a cautious yes, but not yet convenient. But that's definitely on the roadmap. Probably not as high a priority as supporting data and some other things that would be.
You'd sort of have to give people turn by turn. You'd basically give control to one of the multiple users at a time, or some damn thing. It'd be.
Oh, well, then there is the question of a networked game.
Yeah.
You might have to write your own. That's probably a situation where you'd want the server, because as you say, you've got to have some way to kind of globally advance the clock. I can't think of a clever way to do that by coordinating the individual client browsers without writing some additional web code to somehow sync things up. Can probably be done. I just don't know how to do it.
It occurs to me that we've got about 20 minutes left in the time that we would normally be doing
for the second slot.
Yeah, we've managed to get pretty much 2 talks out of you, Tom, back to back, and I appreciate that very much, that you're willing to do that, or that you were even available to do that. That wouldn't have been guaranteed at all. But I do want to make sure that other people who've come in, maybe gotten a little less than what they'd hoped for, to know that they can probably watch this recording at some point and watch the earlier stuff, which was quite interesting as well. But are there questions that are coming up for others in the room? Let's just make sure people get a chance to get. Interaction is always the best part of these talks.
I'm kind of curious, maybe to poll the room, how many of you worry about these kinds of problems of different levels of aggregation and are interested in kind of moving closer to SD or to agent or hybrid agent models, or if there are other things that are bigger problems for you?
I'd push that back to you. Excuse me. I'll let Tom talk, please. I'll ask mine later.
Yeah, just from my perspective, I find this extremely interesting for several reasons. Separating data, model structure, but also being able to, let's say, generate structure on the fly. I think this is highly interesting. I have to admit, I still have to wrap my brain around Ventity still after several releases. So it would be good if we could do some kind of interactive working sessions like you did at the conference, etc. I think this would be highly interesting. What you showed today I found particularly interesting, because I think this gets you actually one step closer to an kind of a pure agent-based model, probably with a little bit less effort, and that's something I really would like to explore. But the categories of problems we could solve with that is actually there. So there are several cases in marketing, in life science, etc. So really much appreciated.
Right. I mean, one of the things we discovered in doing a lot of work for pharma companies and various things was that unfortunately, individual medical histories mattered quite a bit. So I'm trying to think of an example. In mental health, for example, for depression and bipolar disorder and other schizophrenia, the kind of the severe diseases, medications play a pretty big role. Maybe you could probably argue about that a lot, but it was certainly our observation working with some big data on that where we had actually millions of patient records. Unfortunately, this was pre-Ventity, but what we found in that case was that individual histories mattered. It mattered whether somebody had been on 1, 2, or 3 antidepressants, and it might even matter which one, what the order of those had been in terms of kind of governing their future perception of their own mental health state and their propensity to comply with the medication protocol and their frequency of extreme events. So that was a case where we did agent models we did visualization, we did them in Vensim, and we did them we did some kind of raw data analysis. Would have been great to have Ventity at the time that we were doing that, because we could have had individuals in the model with kind of a transaction log that kept track of their recent medication history and their recent compliance with doctor visits and things like that. It would have been great.
Tom, I'm curious about performance and whether you've compared building models using Ventity with similar models built in other languages or Python or whatever else. There are existing epidemiological models, for instance, that are very similar structurally to what you've described.
Right. I'm not sure. We haven't done comparison with, say, doing the same thing in Python or C# or whatever. So I don't really know the answer to that. My impression is generally that there's more overhead in Ventity. So an entity is kind of heavyweight in a sense. So here's a deer that has 4 or 5 states, and I can there's a bunch of infrastructure that gives you access to all of the individual deer, and there's a bunch of infrastructure for, say, creating sub-collections of deer. So for example, in the cohort version of this, you see there's a cohort deer entity, which is this structure. And then there's some collections that aggregate them up by region and sex, or just by region, and you could do just by sex. And within those, we're calculating aggregates. So here's the regional sum of healthy deer. And all that stuff is running all the time, which has a huge benefit, which I think is kind of essential actually, which is that you can always see everything that's going on in the model just by, say, right-clicking something and generating the plot. The downside of that is there's more computational load to those entities. So if you wanted to build a model that had, say, 330 million people in the US in it with an explicit social network, I think Ventity would, and actually the national labs have done this, Ventity would probably grind to a halt on that because it would take a ton of memory, and computation's pretty fast because it's compiled, but I think you'd still have speed issues as well, and it doesn't currently do, high performance computing support to break up the model and execute it on a network of computers or something. So there's a boundary somewhere where you might be driven from Ventity to a traditional programming language environment in order to have some efficiencies. I think that boundary is probably at around 100,000 entities. So we were really targeting situations where you have, say, healthcare payers and providers where the numbers are in the tens to thousands. We weren't targeting things with millions of entities as kind of the use case for this. But I'm not sure where between those poles where the trade-offs start to drive you to other tools. The problem with going to other tools then is you lose your dimensional consistency checking, you lose your model diagram correspondence, although you can kind of use code browsers to do some of that. So there are big trade-offs to consider there.
Hey, can I throw it back to you? Because you said you have a bias towards simple aggregate models, and you've actually done quite a bit of experimental exploratory modeling to try to answer the question, when can we comfortably or shall we say, honestly, use aggregate models? And you didn't really tell us what the answers were that you found out in those exploratory efforts. Or maybe I just didn't hear it.
Oh, well, I guess I'm not sure there is sort of a closed form solution to that. But in this work on chronic wasting disease, we did go with an aggregate representation. So we have, it's sort of a hybrid. So we have deer disaggregated by sex, because you need to know, bucks and does have different effects on reproductive potential, and hunters treat them differently. We also have them disaggregated into 4 age classes. Again, partly it's reproduction, and it's partly the way hunters treat them, and it's partly disease progression. And then we had 4 representative regions with essentially different initial levels of prevalence. So we had kind of the endemic core where disease prevalence is very high, and then sort of the leading edge periphery of that, and then new hotspots and uninfected areas. That aspect of it is much less satisfying than having an explicit spatial model. But the problem is the spatial network has to be pretty fine to be worthwhile. So we were working in Wisconsin, you'd have to get down to the township level. A township is 36 square miles. And there are 1,500 townships roughly in Wisconsin. And, each one. Sorry, I just got muted. There we go. Each one has 9 neighbors, and so the model would become enormous if we did the full spatial version. So I think it's not completely satisfying, but we've elected to go with an aggregate representation on that dimension. I guess I'd add to that it's not so much that one is right or wrong, but that certain kinds of insights are accessible from the aggregate representation there are more that are accessible from the spatial representation. But it's not that the aggregate model is wrong, although there might be other cases where you could argue that an aggregate model was explicitly wrong because of some nonlinearities or something.
It sounds like good advice would be to try to come up with practical tests of the level of aggregation that can be trusted in a given situation.
Right, and that was the motivation for building this model, was so that we could compare aggregate and disaggregated in the same setting. And we actually did several flavors of this for different purposes.
Could I ask how many power users exist for Ventity, that to your knowledge?
I'm not sure, actually. I think it's a small number. So a couple dozen, maybe. I saw a finger up a minute ago. I don't know if there was another question. Go ahead.
Hi. Hello. Hi, Tom. Nice
Hi.
presentation and very interesting. I'm just curious that in a specific, say, small population, this is a very effective model, since it is constantly analyzing, collecting, as well as analyzing and predicting the running history in that way. Now, when we actually extrapolate it to many towns, say in a country setup, then different centrality, the degree centrality is coming up. So one node has many like links. So one town has maybe 10 links, and the other town, say X town has 10 and the Y is 5, or maybe
Right.
Z is 20. And then all this, so degrees, with this different degree centrality, when these are coming, then how, I mean, one single, say, the entirety of the agent, that ad hoc model will actually, how will we consider this in the ad hoc model?
So
Especially because it is then this like coming up and down, coming up and down. Thanks.
right. So it actually, and that shows up in this context as well, because, you know, I mentioned if you wanted to make the model spatial, you'd have to get down to the township level. So with a grid cells that were 6 miles on a side, connected to 9 neighbors. But actually the connectivity is not uniform, because you have natural barriers like rivers and highways, and you have you know, different conditions on the map, different vegetation, urban versus rural, and so on. So if I were extending this to the spatial context, I think I could probably repurpose the cohorts as spatial cells, and I'd normally want to supply that with data from the actual system that captured that connectivity or lack thereof. And I guess same thing in the person version of the model. You could supply data to describe the explicit network topology that you had, or you could even supply several versions of that. One of the things I'd like to have here is sort of a topology builder that would let you easily construct different network architectures for the entities in the model. We don't currently have that. You can do it with actions, but in the infection model with individual people in it, it took me some time to set that up. There's kind of a reusable pattern there now, but you'd have to set it up again manually to do it in another context. But I should mention one other thing kind of related to that is that Ventity has pretty extensive data capabilities. And I'm looking for the model here. In the chronic wasting disease work, we actually ended up hybridizing Vensim and Ventity. So we did the dynamic model in Vensim ultimately because it was aggregate and we wanted to deploy it on the web. But we did all our data modeling in Ventity. So we used it as a repository because it made it easy to slice and dice all the data that we collected from the agency we were working with. The nice thing is you can, so what you're seeing on the screen is a bunch of data variables basically. And you can quickly filter the data according to the attributes of it. So for example, you notice all the charts just changed because I'm showing different subsets of the counties of Wisconsin. And so this became a very convenient tool as a data browser and sort of pre-processor so that we could test different levels of aggregation in the data and then feed that into Vensim for calibration of the model under different aggregation assumptions. And it also gives you quick access to the underlying data. So all the data that's on the screen here is coming from a series of linked spreadsheets. And you can just launch those spreadsheets by clicking on them from inside Ventity. So it's pretty quick just to kind of browse to the source. So you can see a list here of 15 or 20 spreadsheets that we're using to drive the model. And then there's also some GIS capabilities. So you can look at the fraction of deer that are positive and see how the infection is spreading over time. This is at the township level over the sort of the network of grid cells.
Hey, Tom, I think you could keep going for another hour probably, but I think
Yeah.
it's time. I think it's time to just call a halt and say thank you so much for sharing what clearly is a very powerful extension that does build and preserve as much of Vensim as possible, but gives you a whole lot of new capability that you're still figuring out all the wonderful things it can do and any limitations that you may have uncovered. So I just wanted to say thank you, and I'm going to go ahead and turn the recording off. And if people want to hang around, the room's not going to close right away, but I think we ought to call it good for the recording.
All right. Well, thank you everyone for coming and for interesting questions. And I'd be happy to talk more about this another time or get you pointed in the right direction if you're trying to start on a new problem. Thanks,
you.
everyone.